Hello everyone. Here is a new topic: rearrangement of series of real and complex numbers. Definition: let F be a mapping from n to n, where n is a set of natural numbers, be one function. Let summation an, where n going from 1 to infinity, and summation bn, where n going from 1 to infinity, be two series such that bn equal to afn for n belonging to natural number. Now this fn is nothing but your natural number. See, if you apply a mapping, your mapping is from n to n. So for any natural number, f of n will be also coming to this set of natural number, that is your codomain. So f of n is nothing but your natural number, right? So bn is equal to afn for n belonging to natural number. Then summation bn, n going from 1 to infinity, is said to be rearrangement of summation an, n going from 1 to infinity. It will be more clearer when you see this. Summation an equal to what? a1 plus a2 plus a3, so on. If I rearrange the terms, I took a3 to be in the first position and a4 to be in the second position, or rearrange the terms, I will be getting which is equal to a3 plus a4 plus a1 plus a2, so on. Any rearrangement you can choose of your choice. This is equal to, let's say this a3 to be equal to b1, a4 to be as b2, a1 to be as b3. Let's name them as b1, b2, b3. After rearranging the terms of the series a1 plus a2 plus a3, after rearranging the terms, I named these terms to be as b1, b2, b3, a new series which is summation bn, right? Where b1 is a3, b2 is a4, b3 is a1. Thus, summation bn is an rearrangement of summation an. Now is it clear what is bn equal to afn? Fn can be a3, a4, a1, a2, a6, a7, anything. So I just name b1. Suppose I take n1 to be as 1. This b1 is equal to a f of 1, which can be, f1 can be anything. So I named that f1 to be as a3. b1 is af1, b1 is a3. So take this f of 1, suppose it is 3. Then again, what is b2? This is af2. And I name f2 as a4. Sorry, 4. So this b2 comes out to be as a4. So on. So this is nothing but the rearrangement of summation an. This is your subscript only, okay, which denotes the natural number, okay? Right. Now we are having a theorem. We have to prove this theorem. What the theorem says: let summation an, n going from 1 to infinity, be an absolutely convergent series having sum s. Then every rearrangement of summation an also converges absolutely and has sum s. So it is given that we are having this sum to be absolutely convergent and this summation is having the sum s. So after rearranging this, that rearrangement of summation an also converges absolutely and has the sum s. We have to prove this. For that, we again have to define a mapping from f n to n, be 1-to-1 mapping, 1-to-1 function. And we also have to define the sequence bn defined by this bn is equal to f of not f of but fan, right? For n belonging to the natural number. Oh, oops, I'm very sorry. I'm very sorry. This is AFN. So sorry, dear students. Alright, then what is summation Bn? It is an rearrangement of sum An. Fine. Okay. Then what I will do, let's check the mods. B1. I'm taking the mod of sum of the first n terms, right? Not all the infinite terms, just first n terms. Let's check this mod. This is equal to mod of B1. This is, if Bn equal to AFN, then can I write B1 as AF1? Okay. This will be AF2 and Bn will be mod of AFN. Fine? Okay. Now, because this is the sum of finite terms, this sum can be less than equal to summation I, because I have already used n here, so I am writing from k1 to infinity mod of ak. Yes, this is less than equal to this, and this infinite sum is given to be as s. It is given to us that this sum is s. Infinite sum of ans is s. It is given. Now, what this first sum of first n terms is now? It has a bounded partial sums. So from here we get, because this sum is less than equal to some number s. So what we get? We get, whenever this thing happens, we say that mod Bn has bounded partial sums. Fine. Thus, obviously then, this Bn summation is converges, because whenever mod of Bn summation, it has bounded partial sums, that means summation Bn, the given summation Bn, converges absolutely. It is a theorem. So first part is over. What is the second part? We have to prove that this rearrangement summation Bn is nothing but the rearrangement of summation An. Now first part is proved that this summation converges absolutely. What is the second part? The remaining part to be proved is this summation, this rearrangement of An, that is this summation Bn. This has the sum s, right? Now remaining the left part to show summation Bn is equal to s, the same sum s. This we have to now show. Alright. Let take Tn to be equal to B1 plus B2 plus B3 up to Bn. Again I take sum of first n terms, and let's take our Sn, because sum of infinite terms for summation An is s. So sum of first finite n terms, I take that sum to be as Sn for An. A1 plus A2 plus A3, so on. So for Ans, I am taking the first n terms, sum of first n terms to be as Sn, and for bn's I take sum of first n terms to be as Tn, right? Now what is given? Because it is given that summation an where n going from 1 to infinity converges absolutely, this means we know that this sum Sn is converging to S, because it is given that the sequence, the series having the sum S. That means it is converging to S. So let's write the definition for this convergence. For given epsilon positive, there exists a positive integer n such that taking mod Sn minus S. This is nothing but I'm writing the definition for this convergence. This is strictly less than epsilon by 2. I choose such an epsilon such that this thing happens for n greater than equal to n, right? Now this holds for n greater than equal to n, either strictly greater than n or equal to n. This inequality holds. So I take in particular for n equal to capital N, I'm taking in particular. So mod of S capital N minus S. This is strictly less than epsilon by 2. Remark this as 1. Now what is given to us? Since summation an and going from 1 to infinity equal to this is given, what implies this? Now I take S to be on the other side. Sum an minus S. This will be equal to 0. So I write this 0 to be on the left hand side. Nothing matters. Okay. Let's take this sum. Let's look at this sum as, this sum is from 1 to infinity. What I'm doing, I'm taking sum for the first n terms. First n terms, for first n term sum is Sn, right? Plus rest of the sum, which starts from n plus 1 to infinity. An, then minus S. Is it clear to you? See, this sum is what? A1 plus A2 up to An, then further up to infinity. First n terms having the sum Sn. This we have let. Plus rest of the terms will start from n plus 1 to infinity. Right? Now this thing is clear? Okay. In particular, you can take small n to be as capital N also. So, okay. This mod will be greater than equal to mod sum n going from n plus 1 to infinity An minus, just separate them into parts, S. Because I used capital N for small n in particular, so I must write here Sn. That sum to be as Sn. See, A1 plus A2 up to An is S small n, but I take in particular n to be as capital N, so A1, A2 up to this capital N is Sn. Then further more terms for An plus 1, then An plus 2, so on. Clear? That's why I write here Sn, capital N. How this step come? Because we know that this identity, that mod of A minus B is greater than equal to mod A minus mod B. So I took this term as 1 and Sn minus S as the second term. I use this identity over here, right? Okay. Now this thing is what we get. Take mod Sn minus S to be on the other side. This is greater than equal to summation and starting from n plus 1 to infinity An, this mod. This implies summation and going from n plus 1 to infinity An less than equal to Sn minus S. Now what this mod of Sn minus S? This is strictly less than epsilon by 2, which is from 1. We have marked that equation as 1 from here. Okay, fine. Now remark this as 2. We will use this later on. Now let's choose capital M so that this set 1, 2, set of natural numbers. This is subset of F1. I am taking the subscripts, right? F3 up to Fm. I choose such M such that this thing happens. These are also nothing but the natural numbers, you know that. Then this n is greater than m, and because this is a finite terms, right? So my small n can be greater than this capital M. If you are having the finite number of terms, see, F1, F2, F3, Fm, these are the natural numbers, the subscripts. Okay, suppose you are having the finite number of terms B1, B2 up to Bn. Finite number of terms. This can be a subset of the, this is nothing but the rearrangement of the summation An. So B1 can be A6, B2 can be A1, anything, it can be anything. So I choose such M such that I can have this small n, because this n is a natural number which also tending to infinity. So for that M I take, my n can be greater than such M, right? And for such small n, we have mod Tn minus Sn. Let's check this mod. We need this mod later on because I have to prove what? I have to prove Tn tending to S. Tn is nothing but the sum of summation Bn. I have to prove that this sum is having the sum S. This I have to prove. So I need this mod for that. So let's check what this mod is. What I have taken Tn to be equal to? B1, B2 plus B3 so on up to Bn, right? Minus, what is this S of n? This is A1 plus A2 plus A3 up to An. Clear? Okay. What is B1? This is AF1. B2, this is AF2, so on. Bn, this is AFN. Minus, this is A1 plus A2 plus A3, so on. Clear? Now, this sum is for the finite number of terms. Okay, so we are left with finite terms from n plus 1. But because this summation is for the infinite number of terms, hence this mod should be greater than equal to this, right? Or this thing is less than equal to summation and going from n plus 1 to infinity an, right? This is for infinite. This sum is for this sum goes to, or this sum is for the terms which are up to infinity. So obviously this is greater than that. So this is further strictly less than from 2. We have proved this mod to be strictly less than epsilon by 2. Right? Thus, what we get, Tn minus Sn is strictly less than epsilon by 2 for n greater than m. Mark this as 3. Now the final thing which we have to prove is now here. I have to prove this Tn should tends to this S. So let's check this mod Tn minus S. Tn. Just add and subtract, because I have to use this Tn minus S and capital. Just add and subtract this S capital N minus S. Right? This is less than equal to mod Tn minus Sn plus mod Sn minus S. This is strictly less than from 3 epsilon by 2 plus this is nothing but the definition for the convergence. It is given that the sum, this Sn is converging to S. See, from first this thing, this is less than epsilon by 2. So which is equal to epsilon for n strictly greater than m. So thus what we get, Tn minus S is less than epsilon for n strictly greater than m. But epsilon was arbitrary. Very good. So therefore, this Tn converges to S. Thus, summation Bn, the infinite series, the sum of the infinite series is equal to S. Hence the result. Because conversion of mod An implies convergence of An. Okay. So hence the result. Next time we will do Riemann theorem, and that is also a very important one. Thanks for watching this video. Have a very nice and blessed day. God bless you all.